Okay, we're now looking at the key concept on what an exponential decay function looks like, and then we'll be heading into example 4 for Unit 3, Lesson 1. So an exponential decay function is a function that looks like some number b to the x power, and the number b is going to be between 0 and 1. It looks like this. The y-intercept of this graph, the basic graph, will always be 0, 1, and that could change obviously if the function shifted left or right or up or down. And then points along the graph are 1, like 1 comma b is always a value, so whatever the b value is, that will be a coordinate point. For example, if it was 2 to the x, 1 comma 2 would be a point. And similarly, negative 1 comma 1/2 would be another point that shows up on the graph. So let's apply this concept to looking at example 4 now. And for example 4, we have to graph the function 1/5 to the x power and then find the domain and the range. So we're basically just making a table of values again. Remember that if x is 0, y is going to be 1, because 1/5 to any power to the 0 power is always going to be 1. Any number to the 0 power is always 1. When we plug in 1, we get 1/5. When we plug in 1/2, we get the square root of 1 over 125. When we plug in 2, we get 1/25. So you can see these y values are really small really quickly for the x values that we plug in. And similarly, for negative x values, the y values get large very quickly. So now we're just going to plot those points on a graph. And we see this function is what shows up. The domain, just like the other functions we looked at earlier in this lesson, is always going to be all real numbers. And based on the sketch of your graph, you can see that the range will be all the y values greater than 0. Okay, part B, now we have a translated function. We have negative 4 times 1/2 to the x minus 1 power plus 2. So this is a transformation of 1/2 to the x. The negative sign in front means the graph is flipped over. So this negative, we're going to flip the graph over. The 4 means that it's stretched by a factor of 4. We're also going to look at the exponent, which was x minus 1. Because it was minus, that means we're translated right 1 unit. And it had a plus 2 at the end, so k is 2. So the graph is shifted up 2 units. So our basic graph would have been at 0, 1, but we're shifted right 1 and down 4, or up 2, 1, 2, and then we're flipped over an axis, so the points actually get flipped down here. If you wanted to find the y-intercept, you would just plug in when x is 0, simplify this expression, and see what y value you get, which looks like we're going to get about negative 6 over here. The domain, again, is all real numbers, and the range is all y values less than 2. Okay, we got to check your progress problem. You need to graph the function y equals 1/2 to the x. Pause the video, work on your answer. When you have the answer, go on and advance to the next screen. And the answer this time is choice A. And you can see that choice A is the only graph that is a decay graph that has the range values of greater than 0. Okay, now we're looking at part B for the check your progress. We have the function negative 6 times 1/3 to the x minus 2 power minus 3. So think about the transformations that are evident in this equation. When you have your answer, go on to the next screen. Okay, our answer this time is choice A again. Alright, for example 5, we're looking at a real-world problem on air pressure. It says the pressure of the atmosphere is 14.7 pounds per inches squared at Earth's surface. It decreases by about 20% for each mile of altitude up to about 50 miles. Draw a graph to represent atmospheric pressure for an altitude from 0 to 20 miles. So we're going to work off the equation A times 1 minus r to the t power. A is the initial pressure at the Earth's surface, which is 14.7. And the pressure decreases by 20%, so that's our rate. So we're going to do 1 minus 0.20, which gives us 0.80. And then we're using t as our variable. And t is going to represent the miles of altitude. So we're going to use a calculator to graph that because it's not super obvious what that's going to look like. So your calculator should give you a picture that looks something like this. And then remember that our x variable is altitude and our y variable is pressure, air pressure. Part B. Now we're going to estimate the atmospheric pressure with an altitude of 10 miles. So same equation, we're just going to be plugging in 10 for t as our exponent. When we do that and just dump that in the calculator, you're going to get 1.58 pounds per inches squared. So that's the pressure of the atmosphere 10 miles off the surface of the Earth. Okay, we're going to do a quick check your progress problem. This time we have the pressure of a car tire with a bent rim is 34.7 pounds per inches squared at the start of a road trip. It decreases by about 3% for each mile driven due to a leaky seal. Draw a graph to represent the air pressure for a trip from 0 to 40 miles. Pause your video when you have your answer. Go on to the next screen. Okay, our choice this time for the graph is letter B. We're going to look at part B now. We need to estimate the air pressure of the tire after 20 miles. So you're going to set up your equation. Remember, A is the initial pressure, and then you're going to plug in the rate, do 1 minus the rate, and the pressure is going to be the variable in the exponent. All right, our answer this time is choice D. You should have set up an equation that looks like y equals 34.7 times 1 minus 0.03 to the 20th power. And that will give you an answer of 18.87 pounds per inches squared. All right, that's the end of Unit 3, Lesson 1 on graphing exponential functions.